Without objection, the chair is authorized to declare recess at any time. Good morning. Welcome to today's hearing entitled Research and Innovation to Address the Critical Materials Challenge. I know that we are the primary focus of everyone on Capitol Hill today, of all days, and I appreciate you all for joining us. Today, we will be holding a hearing on the importance of rare or difficult to obtain materials, often called critical materials, for a wide array of energy, defense, and research applications. We'll examine a draft bill by my colleague, Mr. Swalwell, that would support critical materials research to improve their recycling and their ability to be replaced with more commonly available materials. Many of the energy technologies that we're all used to that enable our modern life, including clean energy technologies, are underpinned by a host of these critical materials that are found in very limited quantities and in very few countries. This includes important technologies like electrical vehicles, solar panels, wind turbines, and other technologies used by our military and our national infrastructure. So if we continue the success of these technologies, we have to have an affordable rare earth supply chain of these critical materials. Unfortunately, the U.S. now relies on the importation of 100% of 14 of these materials, and importing a partial supply of many more. The supply chain and technology application for each material is different, but it is not wise for us to rely on countries that may be adversarial to us. To address this issue, DOE and the Critical Materials Institute are working hard to develop new sources of these materials. Experts at the National Energy Technology Laboratory, including their great team outside of Pittsburgh, are looking into ways to extract rare earth elements out of coal and coal byproducts. And on my several visits there, they are always proud to show off a beaker of graphite solution extracted from coal that is worth about $20,000, just about this much of it. So it is possible to do. We just have to find a way to make it more economically viable. But this would provide a new resource for places like Western Pennsylvania and beyond. Behind the scenes of the research, the scientific community's work is the need for helium, which is sometimes considered a critical material, and one that we do produce here in the United States. Due to its unique chemical properties, helium is essential for maintaining equipment at hundreds of labs across the country, and it's an important input into industrial processes like rocket propulsion. Recent helium price increases have hampered our lab's work by postponing research, shifting research priorities, and at times harming equipment, all of which strain labs' budgets and slows innovation. We have to ensure that our researchers have access to the helium they need, and federal support can play an important role here. Like with other critical materials, R&D can play a significant role in improving our helium use efficiency, finding new sources, and developing substitutes where possible. We've heard many times on this committee that our economic competitiveness is driven by our support for innovation, which makes this one of our top priorities. We are not guaranteed the materials to continue to research, build, and deploy the next generation of clean energy just because we have the knowledge to develop them. Accordingly, we have to strengthen our supply chain and make sure that we can safeguard our energy future, our national security, and our economic growth. That's why I'm excited to hear more about this topic, and I thank our panel of witnesses for being here today. With that, I will turn to the ranking member, Mr. Weber, for an opening statement.
Thank you, Chairman Lamb, for holding today's subcommittee hearing. I'm looking forward to hearing from our witnesses about the energy technologies and applications being developed through critical materials research. Critical materials, as you already pointed out, play an important role in supporting the technology that will ultimately help us change the United States' energy consumption. Whether it's lithium used in advanced batteries or helium, yes, helium is more than just party balloons, in case you were wondering. In rocket propulsion systems, our resources are limited in quantity and can be challenging to develop. And while demand is only increasing for these critical materials, supply can also be and is often restricted by geopolitical and market forces. As it currently stands, Australia, Chile, China, and Argentina produce 97% of the world's lithium supply, a mineral that is absolutely essential for battery technology and will be key for the expansion of electric vehicles. So imagine if our adversaries controlled a critical material used in building the next advanced military weapon. If they were to slow down that supply or cut it off altogether, we would be at a dangerous disadvantage. Energy is just as important, and we cannot allow the advancement of technology to be limited by political or geographic forces. In order to understand our economic risk, it's vital that we assess our resources here in the United States and better understand exactly what elements and materials are vulnerable to global supply disruptions, no matter what the source. So that is one of the reasons President Trump issued Executive Order 3817, and the Department of Interior took the first step by leading an interagency coordination to publish a list of 35 critical minerals to the American economy. But understanding our natural resources is only a part of the story. Because many critical materials are very difficult to produce, it is absolutely essential that we maximize our ability to not only use but to reuse these materials. By extending the commercial life cycle of these materials and investing in research to improve the efficiency of recycling and reuse, we can maximize our resources. Research can also allow us to explore opportunities to extract critical materials from new sources that were once considered, quite frankly, only waste products. We actually talked a little bit about that. That is why DOE's National Energy Technology Laboratory, in coordination with the Critical Materials Institute, or CMI, is currently conducting research on extracting materials from coal and coal byproducts. This research can help improve the economics of energy supply and production and reduce those very environmental impacts we all want to reduce. And at Ames Lab, which hosts CMI, researchers are working to improve reuse and recycling and to expand our supply by synthesizing new materials or developing substitutes. By coordinating basic research in materials science and chemistry with early-stage applied research in manufacturing, the CMI structure helps us to get the best bang for our buck and takes a holistic approach to this challenge. Our national security and our economic growth cannot be left at the mercy of a global supply chain. It just cannot happen. I believe the Department of Energy has the capability to conduct the research and development needed to get the United States back on track as a global leader in critical materials. Dare I say that the United States leading in critical materials is our critical mission. I look forward to hearing from our witnesses on how their research is contributing to this goal and what steps we as Congress will need to take to support those efforts. Mr. Chairman, I yield back.
Thank you. Okay, no, we don't have either of them here. Okay, never mind. At this time, I would like to introduce our witnesses. Dr. Adam Schwartz is the director of Ames Laboratory, one of DOE's 17 national labs. Ames Lab stewards the Critical Materials Institute, a DOE energy innovation hub dedicated to researching key critical materials. Dr. Schwartz is also a professor of materials science and engineering at Iowa State University, and previously spent 23 years working at Lawrence Livermore National Laboratory, researching topics such as physical metallurgy and condensed matter physics. Welcome, Dr. Schwartz. Dr. Sophia Hayes is a professor in the Department of Chemistry at Washington University in St. Louis, covering research topics in chemistry, materials science, and condensed matter physics. She is also a co-author of the 2016 report, Responding to the U.S. Research Community's Liquid Helium Crisis, and uses helium extensively in her research to maintain equipment and achieve very low cryogenic temperatures. Welcome, Dr. Hayes. Mr. David Weiss is the Vice President of Engineering and R&D at Eck Industries, which is based in Wisconsin and produces advanced metal castings. In his role, he is responsible for the research and application of high-performance alloys and casting concepts, also the subject of over 80 papers that he has authored or co-authored. During his time at Eck Industries, the company has worked closely with DOE's Critical Materials Institute. Welcome, Mr. Weiss. Dr. Carol Handwerker is the Reinhardt Schuhmann Jr. Professor of Materials Engineering and Environmental and Ecological Engineering at Purdue University and leads the DOE Critical Materials Institute's focus area in recycling and reuse. Prior to joining Purdue, she served as the chief of NIST's Metallurgy Division. During her 21-year career at NIST, she led measurement R&D to improve the manufacture and performance of electronic, magnetic, photonic, and structural materials. Welcome, Dr. Handwerker. As our witnesses should know, you will each have 5 minutes for your spoken testimony. Your written testimony will be included in the record for the hearing. And when you all have completed your spoken testimony, we will begin with questions. Each member will have 5 minutes to question the panel. We will start with Dr. Schwartz.
Chairman Lamb, Ranking Member Weber, and members of the subcommittee, thank you for the opportunity to discuss the importance of research and innovation to address the critical materials challenge. And thank you for your continued strong support of physical sciences and energy research. I'm Adam Schwartz, Director of Ames Laboratory, Department of Energy National Laboratory, managed by and co-located on the campus of Iowa State University. The United States is a world leader in physics, chemistry, and materials research as a result of decades of federal investment. To remain a world leader, the U.S. must continue to innovate with new materials, new products, new energy options, and new defense applications. However, new technologies and engineered materials create the potential for rapid increases in demand for some elements, thus creating the next critical material. A critical material provides essential functionality to modern engineered material, has few ready substitutes, and is subject to supply chain risk. As with most things we don't have enough of, the choice is to make more or use less. There are 2 substantial DOE programs currently addressing the criticality of rare earth elements. DOE's Office of Fossil Energy and the National Energy Technology Laboratory aim to make more by understanding the technical and economic feasibility of extracting and recovering rare earths from coal and coal byproducts, such as coal refuse, power generation ash, clay and shale, and acid mine drainage. Projects range from fundamental research to the design, construction, and operation of small pilot-scale facilities producing saleable, high-purity rare earth oxides. The second major program to reduce criticality comes from DOE's Advanced Manufacturing Office. The Critical Materials Institute, or CMI, is conducting early-stage research to accelerate the development and application of solutions to critical materials challenges, enabling innovation in U.S. manufacturing and enhancing U.S. energy security. By closely following the DOE strategy to make more by diversifying supply and improving reuse and recycling, or use less by developing substitutes, the CMI team of national labs, universities, and industrial partners is having an impact. With 309 publications, 129 invention disclosures leading to 58 U.S. patent applications, 12 awarded patents, and 9 licensed technologies. As examples, CMI research to diversify supply aims to increase the supply of critical materials by creating more cost-effective and energy-efficient methods for the extraction, separation, and conversion of ore to metal. Momentum Technologies, a U.S. startup company, licensed 2 of those CMI technologies. To improve reuse and recycling, CMI developed an innovative acid-free dissolution and separation process for removing rare earth ions from shredded hard disk drives. That process won an R&D 100 award. And for developing substitutes, a newly discovered permanent magnet formulation replaces half of the precious neodymium, effectively doubling magnet production per ton of ore. The CMI Materials Criticality Framework is being extended well beyond rare earths to include materials for battery and thin-film solar and LED panels. The push toward electric mobility increases the demand for energy storage elements like lithium, cobalt, and graphite. CMI research has developed technologies that can allow domestic production of 2 novel sources of lithium from geothermal brine and mining tailings. In addition to all the successes and options that CMI has generated, the most important of all is the enduring capability that the team has created. It is the combination of criticality assessments, techno-economic analyses, road mapping, and early input from industry that sets the stage for effective and efficient research into solving critical materials challenges. CMI's Critical Materials Framework integrates expertise across the supply chains to deliver industrial-relevant technologies to diversify supply, improve reuse and recycling, and develop substitutes that are all informed and enabled by foundational science. It is this enduring capability and collaboration that puts the U.S. in the strongest position as new materials become critical, and is why CMI in particular is such an important national resource for addressing these challenges that are only going to grow more pronounced over time. Global factors such as growth in world population will place an even greater stress on diversification of mineral resources, the importance of innovation in creating substitute materials, and the development of the science to improve the economics of reuse and recycling. Thank you for the opportunity to testify, and again, thank you for your consistent, strong support of materials and energy research. I'd be happy to address any questions or provide additional information.
Thank you, Dr. Schwartz. Dr. Hayes.
Chairman Lamb, Ranking Member Weber, and members of the subcommittee, thank you for the opportunity to discuss the importance of research and innovation on these critical materials. I'm Sophia Hayes, Professor of Chemistry at Washington University in St. Louis, and as eloquently put by you both, I'm a researcher who uses liquid helium in my own research program for cryogenic applications, as well as to sustain instruments. I'd like to highlight my instruments are not all that uncommon. These are used in every pharmaceutical company, every R&D department of oil and gas companies, commodity chemical companies, and also at every university within the United States that has a major science and engineering program. So imagine a future time when helium is in short supply, where access to such instruments may become more limited or shut down. Medical diagnostic imaging could also become less accessible, and where the latest handheld electronic device also slows in production, all for want of this commodity chemical. So let me share my research community's experiences as a reflection of the broader community's needs. Helium is an element, as you pointed out, with many, many special properties. It's lighter than air, it is inert or unreactive, and it also can achieve low temperatures, lower than any other substance we have on Earth. And instruments like mine require helium to operate. They cannot function without it, but liquid helium evaporates as it's being used, and therefore it must be replenished. What we have faced in the past 2 decades is 2 problems. One is steep price increases, and the other is supply shocks, where helium could not be acquired in some cases at any price. The origin of the price increases come from a market that's highly volatile. At my institution, the price for liquid helium has increased more than 400% during my career, but the grants that we receive remain flat, not accounting for such massive inflation in the price of this line item in my budget. For researchers like myself, it means I have to choose between paying for helium or paying the salary to support a graduate student in getting a PhD. In my case, I've had to decommission magnets, reducing my lab's research capacity. Even more critical than price is supply insecurity. A supply shock lasting weeks or even a month can be disastrous. My magnets need to be filled every 4 weeks, so a delay of even 2 to 3 weeks is a crisis. And importantly, if my supply is cut, it's likely that it's being felt regionally. We've had several major supply shocks in my career, the most recent as a result of the Qatar blockade, and multiple minor supply shocks. Given these, forward-thinking civil servants and some of our professional scientific societies has tried to come to our community's rescue. For several years, the Defense Logistics Agency, in collaboration with the American Physical Society and American Chemical Society, they were able to provide program participants a reliable source of helium at lower prices than they could negotiate on their own, helping to protect smaller-scale university users who receive federal funding. Unfortunately, we just learned this program will be discontinued in January, in part due to the turbulent helium market, showing how incredibly challenging this situation is. This purchasing program helped researchers reduce helium costs and mitigate pricing issues in the near term, but our irreplaceable helium resources continue to be depleted, reducing our long-term use of helium is essential. With this in mind, we must enable as many academic researchers as possible to reduce their helium consumption without compromising their programs, their research programs. National Science Foundation's Division of Materials Research is helping a small number of researchers reduce their helium use and save the government money over time by providing funding for the purchase of helium recyclers. This program is successful but far too modest to address the problems we are facing. In my opinion, the NSF program should be looked at as a model, and Congress should ask federal agencies to support the wide-range adoption of helium recycling equipment. This will require agencies to invest in the capital and equipment infrastructure necessary to make helium recycling commonplace. Unless funding is dedicated to help address this issue, the U.S. risks losing the research capacity responsible for many significant breakthroughs in areas such as medicine, national security, and fundamental science. Additionally, while outside the jurisdiction of this committee, it is important to recognize that the U.S. Strategic Helium Reserve, which is scheduled for shutdown in fall 2021, is a central component of the domestic helium supply. Storage of an inventory of helium is critical for the health of our helium supply infrastructure. Thank you for this opportunity to testify. I and my colleagues will work with the committee at any time now or in the future to help maintain the nation's security and economic competitiveness by ensuring this vital resource is preserved. Thank you.
Thank you, Dr. Hayes. Mr. Weiss.
Chairman Lamb, Ranking Member Weber, and members of the subcommittee, thank you for giving me the opportunity to appear before you today. My name is David Weiss, and I'm Vice President of Engineering and Research and Development for Eck Industries Incorporated, located in Manitowoc, Wisconsin. We employ 260 people in the production of aluminum castings and specialty aluminum alloys. We serve the commercial aviation market and manufacture structural castings for the military, as well as components for heavy-duty hybrid powertrains. The need for improved aluminum alloys that can function at elevated temperatures is important, and our company has been involved in research on the topic since 2003. We considered the use of cerium as an alloy in addition to aluminum since it is the most abundant and least costly rare earth element and theoretically had the potential for high temperature strengthening. Cerium also offers a potential solution to the rare earth supply issue since cerium oxides and carbonates are the primary minerals in many rare earth deposits, particularly those available in the United States, as in the Mountain Pass mine in California. However, much of it is returned to the ground as waste. The development of a substantial use of cerium changes the economics of rare earth production by the beneficial use as a byproduct, thereby lowering the cost of heavy rare earths used for magnets and electronics such as dysprosium and neodymium. In discussion with Critical Materials Institute representatives at Oak Ridge National Laboratory, it was determined that this expanded use of cerium would serve a role in diversifying the rare earth supply base, one of the key tasks of the CMI program. CMI released seed research funding to determine casting characteristics and mechanical properties of aluminum cerium alloy systems, and it was determined that these systems have excellent castability and superb high temperature properties, higher even than the aluminum scandium alloys that we had previously developed. Our company continued to develop the aluminum cerium system with internal funding and with the assistance of national laboratory resources provided in part by CMI. The results were published and presented. The casting purchasing community took notice, particularly after the alloy system won an R&D 100 award in 2017. Eck licensed the technology and continued its development. Materials development is always a complex enterprise. Potential customers look at the data, request samples, do initial evaluation, and look for attributes of the material that had not been tested or had not been considered in the original development. Commercialization requires ongoing research to make a product in volume that meets all the customers' requirements at a cost that they can afford. We are working with 5 different Fortune 100 manufacturing companies to deploy the alloy in key products for their organizations. These efforts, industrial scale-up at our company, extensive product testing by the original equipment manufacturers, and continued research to meet product-specific needs and reduce cost are enabling successful development of aluminum cerium alloys. We have started on a new phase of research that bypasses the need to produce metallic cerium to alloy with aluminum. We have demonstrated that at laboratory scale, we can alloy aluminum with cerium through direct reduction of the cerium oxide or carbonate at a significant savings in energy and cost. This would eliminate the foreign supply chain completely for this element. As we scale this technology, we expect to be able to produce aluminum cerium alloys at the same cost as conventional aluminum alloys. Good research can make unexpected advances. We set out to produce an alloy resistant to elevated temperatures, and we were able to do that. In addition, the alloy is remarkably corrosion resistant, saves energy, and can easily be used in additive manufacturing. Our success to date has been based upon several factors: the extraordinary team of researchers that have been assembled by CMI, very strong industrial participation, and a willingness to continue to support research that gets over the rough spots as our commercialization proceeds. Thank you for giving me the opportunity to address you today and to show my support for additional critical material research funding. Thank you.
Thank you, Mr. Weiss. Dr. Handwerker.
Chairman Lamb, Ranking Member Weber, and members of the subcommittee, thank you for the opportunity to discuss the importance of research, development, and demonstration to the critical materials challenge and how we can create a workforce capable of ensuring the future supply of critical materials for the nation. I'm Carol Handwerker, Schumann Professor of Materials Engineering at Purdue University and the Program Lead for Recycling and Reuse in the DOE Critical Materials Institute. Before joining Purdue, I was at NIST for 21 years, most recently serving as Chief of the Metallurgy Division. Both at NIST and Purdue, I've led industry, government, university partnerships to deliver science to solve national problems that industry could and did adopt. The Critical Materials Institute is a model for how HR 4481 might succeed. Drawing on 4 government labs, 9 universities, and 15 companies, it's managed as a single unified organization, setting joint priorities to ensure critical material supplies by connecting basic science with technology while also developing new researchers and leaders for the future. CMI shares HR 4481's goal, quote, to assure the long-term, secure, and sustainable supply of energy-critical materials sufficient to satisfy the national security, economic well-being, and industrial production needs of the United States, end quote. In CMI, we use 4 key strategies to deliver meaningful impact from early-stage research. The first is identifying the most important challenges and the most effective solutions across the full range of possibilities. The second is collaborating closely with industry from concept stage onward to build solutions that industries can use. The third is delivering quantified economic, logistical, and environmental analyses. And fourth is building teams of the world's foremost researchers to overcome scientific barriers. Every CMI research deliverable fits into a supply chain with the necessary links to industry. One example is a project for value recovery from hard disk drives, which are data storage workhorses of the cloud, and the second largest use of rare earth magnets in the global economy. Billions of hard disks are in use across the United States, and tens of millions of them are shredded each year to destroy the sensitive information that they contain. When that happens, the rare earth elements are lost. CMI, Seagate, Purdue, and the International Electronics Manufacturing Initiative, known as INEMI, have forged a project team from organizations that together can form a complete supply chain to recover viable quantities of rare earths from the magnets in scrapped hard drives. The INEMI Consortium's membership provides industrial skills and expertise that are complementary to CMI's research capabilities. The 15 organizations in the hard disk drive value recovery team include Seagate, Google, Microsoft, and Cisco, as well as the CMI National Labs, Purdue, Momentum Technologies, and Urban Mining Company. The project has identified 5 key approaches to a circular economy for hard disk drives with multiple pathways enabled by CMI's fundamental research. There is a simple key to CMI's most successful projects. We understand that a chain does not exist without all its links in place, and we cannot sensibly build any single link if it is not properly connected to its neighbors. Early career researchers in CMI develop scientific skills and knowledge like any of their peers, but they also see firsthand how seamless collaboration allows great science to emerge from industrial problems. This inspires them to carry forward in this area, and it is one of the hallmarks of CMI. CMI accelerates technology adoption and bridges the valley of death. It's the place, so-called valley of death, where technologies too often die in the transition from early stage R&D to commercialization. Operating with a sense of urgency from the outset, CMI has developed a focused strategy and applied it to a broadening set of energy-critical materials, translating world-class science into commercialized solutions in as little as 3 years. Creating a robust supply of energy-critical elements and products for the United States through H.R. 4481's program of research, development, demonstration, and commercial application will enable economic well-being and industrial vitality in the country to continue. CMI has built great capabilities, research teams, and expertise that are consistent with this goal and are ready to be applied to this effort.
Thank you, Dr. Handwerker. We will begin with 5-minute rounds of questions, and I recognize myself for 5 minutes. Dr. Schwartz, I'd like to start with you. Thank you for giving so much attention to NETL and their program of rare earth research. You mentioned in your testimony the 3 domestic pilot scale operations that they have going on. Would you mind just saying a little bit more about what those are, where they operate, and exactly kind of what they're producing today?
I don't have all the details on that. I can get them for you and be happy to do that. Much of the work has been done, I believe, in collaboration with universities, particularly University of Kentucky, where that team is trying to understand the chemistry and the science and the technologies of extracting those rare earth elements, which essentially start with maybe 300 parts per million of concentration. So in many ways, trying to extract very low abundant elements from whatever product. In many cases, though, for example, the acid mine drainage, those rare earth elements are in a, relatively speaking, a chemically easy way of extracting. So the development of the science and the technology and ultimately the pilot scale project is aimed to extract those elements as efficiently as possible. Again, I don't have all the details, but I'd be happy to work with my NETL colleagues to provide that specific answer.
That's okay, thank you. With the acid mine drainage extraction, I'd noticed also in your written testimony, you characterized that as easy. How would you explain then kind of what barriers remain for the actual commercial application of that? You know, so like for a comparison is, in Pennsylvania, there are companies that make a profit burning waste coal. You know, they've figured out a way to convert that into something that can still produce energy. If it's easy to extract minerals from those same coal piles, sort of what's the future look like in terms of how we might actually get to commercialization?
So I would say there are 2 issues. Both of them deal with the economics.
Would you move your mic a little closer over to you?
2 primary issues, both dealing with economics. One is being able to develop the large-scale processing plant, and the second would be how do you move that processing plant to the location where the acid mine drainage is located or other sources are located. So that may be incompatible. So then the challenge would be how do you develop somewhat mobile units that could move from one acid mine drainage location to another, to another, to another. So the bottom line, I believe, as with most things, it's economics. How do you do this economically? Either develop the chemistry processing, but then also to locate that chemical processing facility or be able to move it to where it needs to be.
Thank you. That's actually the same challenge with people who burn waste coal as the transportation cost is almost everything to them. Thank you.
As with recycling as well.
Yeah. Mr. Weiss, first of all, thank you for being here and for sharing that story. It's such a clear example of success. I was trying to just understand the timeline. Did you first get the Department of Energy grant in 2004? Is that right?
We began work with CMI approximately 5 years ago.
Okay.
So we had done some earlier work on scandium-containing alloys for high temperature applications before that.
I see. So that was
Okay.
kind of a different project.
It's a different project, correct?
I was just sort of trying to understand the length of time from when you started working on the aluminum cerium alloys with
it's-
DOE support to sort of commercialization, what that looked like?
It's been about 4 years.
4 years, okay.
We had our earliest customer about 2 years in, it was an early adopter customer who really was interested in the performance of the material and weren't required to go through a lot of extensive testing. Working with much larger customers, Fortune 100 customers, the testing regime is much, much longer, as you can imagine.
And do you think you would have been able to accomplish this without federal support?
Absolutely not. We can make the castings. We know how to make the castings. We know how to alloy material, but understanding what you have, doing the microstructural analysis, understanding the mechanisms in play in order to understand the strengthening in the alloy, we don't have those capabilities at all, and the national labs have them in abundance.
Thank you. Mr. Weber, you're recognized for 5 minutes.
Thank you. I don't know where to start. This is great. Dr. Hayes, you said, I owned an air conditioning company for 35 years, so all this stuff about energy transfer and Freon and so on and so forth is really interesting to me. You said that you used helium, and you have to, of course, your budget was flat. That didn't escape me. And helium has gone up 400% in your testimony. And then you also said you had to decommission magnets and that they have to be filled every 3 to 4 weeks.
Yes, that's correct.
So magnets use helium.
Indeed. So they're using helium to achieve what's called a superconducting state to create the magnetic field.
Okay. Is that very low cryogenic temperatures?
Yes, it's 4 Kelvin, a very low temperature, about the temperature of outer space as an equivalent. So,
Put that in Fahrenheit for me, will you?
in my written testimony, I believe I have it. It's minus 450, minus 460. around there. I can get you the
I
exact.
keep talking about inches and yards, and my kids keep telling me I have to get in the metric system. You said, get in the metric system, Dad. I said, I'll get there inch by inch. Just don't push it.
Minus 452. is
Minus
the exact.
452. Okay, well, Freon freezes at minus 4 something. I took that class 30-something years ago. You said helium is the most, it'll get the coldest that we have. What's the second coldest?
Oh, good question. I believe hydrogen, perhaps.
Is it hydrogen?
Hydrogen, yes.
Okay.
The molecule hydrogen.
Okay. And I thought you said that helium evaporates as we use it.
It does.
Okay. But then you also said we want to try to collect it. Did I misunderstand that?
No, so what I meant is two things. One is because it's inert, as it evaporates, it escapes the atmosphere. It is, if I'm not mistaken, one of the only elements to do so. So whatever we have here on the Earth that we release is gone. So
It escapes the atmosphere
Yes.
as it goes into outer space.
It goes into
and now
outer
you know why outer space is so cold.
That's very funny.
Yeah.
But by recycling it and keeping it contained, then we can continue to reuse it. Let me give you a quick analogy.
But how do you recycle it, doctor, if when you use it up?
So imagine the radiator of your car. It's like a cooling fluid that can be circulated around and around. Sure, a little bit leaks out and it must be topped off, but
Okay.
that kind of recycling.
But you want a closed loop. Is that helium pressurized? If it's at low pressure, it can be, it's a liquid, right?
It's a closed loop, and
It's a
all we do
closed
is
loop.
recapture the gas, compress it again into a liquid, and then reuse it around and around.
So how do you recapture that gas?
Through piping, generally, and through large bags that can have space to hold all that gas.
Okay. But you wouldn't literally expect for that to be in the radiator of your car because it's too cost prohibitive and too expensive.
Indeed, but
Right.
if we could co-locate helium-using equipment and several
Okay.
users could all
Okay.
use such a system.
You keep calling helium an inert for the audience, inert, I-N-E, or not a nerd. Yes, I'm the nerd here because all this stuff fascinates me about this kind of stuff. So thank you for that. Mr. Weiss, I'm going to jump over to you. You said the need for elevated temperature for aluminum alloys. Again, I was in the air conditioning business. We do a lot of welding, copper, and there's a lot of brazing and stuff that goes on. And you said you were considering cerium and dysprosium. Was that the other one?
Well, cerium is the element that we are using. Dysprosium is too expensive to use.
Oh, I got you.
Right.
So the need for elevated temp. So when you do a high temp alloy aluminum casting, what kind of temperature can you expect to encounter? Is it 200 degrees? Is it 1,200 degrees?
So
Again,
it-
I'm Fahrenheit.
Yeah, so in Fahrenheit, most aluminum alloys lose all of their strength around 300 degrees Fahrenheit. And so what we are doing and what we've indeed demonstrated on these alloys is reasonable mechanical properties all the way up to 600 degrees Fahrenheit.
What application what would that apply to?
Well,
Who would use that?
There's a couple things. The turbochargers, which are getting hotter and hotter as you try to improve engine efficiencies. Things like cylinder heads, as you increase the power density, the temperature goes up. Those would be two of the major potential manufacturers.
Do you sell to the automotive market for like engine blocks, for example?
We do right now, not in aluminum cerium alloys yet, but they are being tested by them.
So is there a higher, and again, I'm just the technical nerd that I am, is that for diesel engines, is that higher than gasoline engines?
Yes, it is, and most of the work that we're doing is for diesel engines currently.
Yeah. Okay, well, I've got other questions, Mr. Chairman, I'm going to yield back.
And recognize Chairwoman Johnson for 5 minutes.
Thank you very much, Mr. Chairman, and thanks to all of our witnesses who have come. I'm a little concerned about some of the reactions, but I do want to, Dr. Schwartz, in your testimony, you discussed both the short-term and the long-term risk of critical materials supply chain. Could you discuss the differences between the two and the possible short and long-term solutions available?
Thank you for the
That
question.
approaches.
Short term, most of those supply risks are political or geopolitical in nature, meaning, and we can use the example from 2010 of the rare earth crisis, where over the previous 30-some years, where in the 1960s, the U.S. used to be the #1 producer of rare earth oxides in the world at the Mountain Pass mine. Over that subsequent 30 years, most of the world's mining, processing, and fabrication of rare earth elements came out of China. Then there was a price spike, which led to increases in prices up to maybe 50 times for certain elements. That is the type of short-term geopolitical risk that could occur in rare earths, as it did previously, or in other materials. Currently, lithium is not produced in significant quantities here in the U.S. Long-term, that geopolitical risk remains if we become, as a country, more reliant on importing of materials like lithium for batteries, or whatever that next critical material could be. That is one source of the long-term risk. The other source of long-term risk is if we, as a community, discover the next great functional material, whether it is for quantum computing or caloric cooling, could be any of that. If that demand for that new technology outweighs current production, either in the United States or in the world, that also sets up for long-term critical materials risk.
Well, how do you think that the research community has responded to this reaction from China, especially in alleviating some of these risks?
So the United States, Japan, European Union have a yearly get-together, the trilateral meeting to discuss critical materials and the response to those critical materials needs. Japan has its approach. European Union has its approach. The United States has focused on its resources on the Office of Fossil Energy, National Energy Technology Laboratory Program to extract rare earths from a known resource we have here in the U.S., and that is coal and coal byproducts. And that team is making excellent progress. They are now to the point where they believe they can make saleable, low-cost, high-purity rare earth oxides. The second major program, Critical Materials Institute, has made significant progress across all of the supply chains, from diversifying the supply, improving reuse and recycling, and in developing substitutes. An example that I put in the written testimony is about replacing some of the more rare earth phosphors in fluorescent lamps. Fluorescent lamps use a triphosphor, red, green, and blue. The red and the blue and the green in particular use those more expensive, heavy rare earth elements. The CMI team created options for that lighting industry that required no rare earths as a replacement for or a substitute for the red phosphor, and only 10% of the rare earths required for the green phosphor. So short term, the team is making significant progress in all three of those areas. Use less or make more. Going forward, it is that combination, it is that teaming of all the expertise. It's not just doing science. It's not just creating the next material, but it's understanding how that research could potentially improve the supply chains, going all the way back to the techno-economic analysis, doing the road mapping, talking to U.S. industries, what is most important now and then in the future. And a coordinated effort, like I think is being done. There's a lot more to do, but that coordinated effort moves us along that path toward addressing those critical materials challenges. It's really that critical material framework that has been put in place over the last 5 years that is now positioned to accelerate development of options for the supply chain risks.
Thank you very much. My time's expired.
Recognize Dr. Baird for 5 minutes.
Thank you, Mr. Chairman, and thank you, witnesses, for being here. We do appreciate all the information you bring us in terms of the latest technology regarding these rare earth elements. And so, Dr. Handwerker, I'm going to start with you. I must tell you that I'm always pleased to see my alma mater involved in the cutting-edge technology, so thank you for being here. My question deals with the comments you made in your prepared testimony. You state that while government-funded R&D usually takes at least 20 years to move from discovery in the lab to success in the marketplace, then DOE's Critical Materials Institute, or CMI, inventions have been adopted by industry in as little as, say, 3 years. In your opinion, what unique role do CMI's academic partners, like Purdue University, play in this success? And then what recommendations do you have for other academic institutions who may want to partner with the DOE Energy Innovation Program?
Thank you. First of all, boiler up.
Boiler up.
At Purdue University, one of our hallmarks is advanced manufacturing. And so much of what we do in critical materials is really focused in advanced manufacturing. Advanced mining is really part of the manufacturing infrastructure of the nation. So at Purdue, one of our key contributions to the Critical Materials Institute has been developing tools to do those economic analyses. We were talking about the logistics analyses that are so important in determining whether a technology, whether it be mining or recycling or reuse, are going to be profitable. So we've created these tools that have taught all across the Critical Materials Institute, we've taught the different project leads all the way down to even undergraduates how to do these economic analyses as they're developing these key technologies. Because if you look at the scientific literature and you want to find, okay, how do you get rare earth materials out of magnets, there are many papers associated with that. There are many papers on that topic. The issue, though, is it can't be done economically with low environmental impact and in a way that actually gets the material, for example, in collection. So one of the things that we've been able to contribute are these economic analyses, life cycle assessments, and also scenario analyses, which are also called out in HR 4481. It's so important to see, all right, how do we mitigate the risk for critical materials?
Thank you. Do any of the other witnesses have an opinion about what areas of fundamental research would provide the highest return on investment? So, Dr. Schwartz, start with you.
One of the biggest bottlenecks right now is being able to separate the rare earths from one another and then to take those separated rare earth oxides and create metal out of it. That is not the environmentally cleanest process out there. So although Critical Materials Institute and researchers around the country are making progress understanding that separation process, being able to take one rare earth oxide out of the collection of rare earth oxides, as Dr. Handwerker pointed out, it's not yet economical. So fundamental and early stage research into those separation processes are, I still think, one of the keys. Critical Materials Institute is doing some, but really not enough work in taking those rare earth oxides and converting it to metal, because that's really, in most cases, the starting point for making materials to be put into systems, to be put into products that are needed for U.S. energy security, national security, and other things. So I think continued focus on that processing required to separate the rare earth oxides from each other, make the metal, and then there are huge opportunities not only for critical materials, but in the areas of recycling. Recycling of the hard disk drives, which Carol pointed out, the recycling of lithium and batteries and cobalt and magnets from the first generation of hybrid electric vehicles, for example. Recycling science has been lagging behind for lots of reasons, including economics, but the science needs to be done to do that, to develop processes to extract those materials economically.
Thank you. And Mr. Chairman, I got, could we have the other two? Do I have time? I'm over my limit.
Sure. I think they can speak quickly.
Thank you.
Go ahead.
I'll be brief, just to say that within the areas of magnet technology, we heard about neodymium from a couple of speakers. This is not part of my written testimony, but there are efforts at the National High Magnetic Field Laboratory to develop superconducting magnets that are based on high-temperature superconductors. They would use different elements, they would have different designs, and we might be able to escape even the use of liquid helium. So that's a new direction that could be pursued, but is not maybe heavily funded at the moment. But those designs exist.
So in response to, you know, how students play a role and how academic institutions play a role, it is interesting to me that having had demonstrated some success in the use of cerium, for example, in materials, there's probably 4 or 5 master's students now outside of the CMI envelope that have looked at that and are looking at various things that we have not looked at in CMI as far as particular mechanical properties or whatever. And so research gains a certain momentum after a certain point, and more people get involved, and that's going to be good for everybody all the way around.
Thank all of you, and I yield back.
Thank you. And I recognize Mr. Foster for 5 minutes.
Thank you, Mr. Chairman, and to our witnesses. Let's say, I guess I'll start with Dr. Schwartz. How do you deal with the fact that you don't really know 10 or 20 years from now which elements will end up being strategic? You know, we're worrying about lithium, and there's an excellent chance that we'll succeed at battery R&D that looks at divalent chemistries, and it's magnesium, which I don't think will ever be strategic, will be the key element in batteries. You know, there are alternative technologies like switch reluctance motors may make rare earth motors irrelevant for many applications. You know, just you mentioned, I think someone mentioned phosphorus for fluorescent bulbs. Okay, they're being replaced by LEDs. I'm not sure whether white LEDs, I know they have some kind of wave shifter, but I'm not sure if that's a rare earth wave shifter, where they get a blue LED and then use a full spectrum. So how do you deal with that? You know, both in the U.S. and in these international meetings.
Dr. Foster, that is a great question. Like so many things, we have good visibility out to the horizon. We know what is coming up. We know that electric mobility is going to be very significant in this country and across the world. We suspect that quantum information sciences, quantum computing is going to be significant at some point. But we don't have visibility across the horizon, and that's why the development of the framework, the processes, the critical materials framework that allows us to take a look at the problem as early as we can, do that criticality assessment where we are trying to look out at new industries of the future to say, this could create a demand for manganese. Manganese could be a great element. Magnesium could be a great element. But until there is a science and technology base, until there are applications beginning to show up, can we say, that could be large. So I think from my perspective, it's developing that enduring capability, that critical materials framework that will be in a position to address the next critical material as quickly as possible when that material becomes critical.
Yeah, and in these international meetings, is there some understanding that the countries of the free world are not going to do what the Chinese did to the Japanese not so long ago and grab them by the neck and try to get concessions on something? Do you think there's a need for some sort of understanding along those lines, at least among the free world?
That's really outside my area of scientific expertise, but I would say yes. Just a few weeks ago, Energy Efficiency and Renewable Energy Office with Advanced Manufacturing Office and the Office of Fossil Energy organized a roundtable and workshop on rare earths. We had representatives from Canada and from Australia talking about those partnerships that will help protect against a single country dominating a material, dominating a market. So I say, yes, there is room for significant discussions to make sure that those partnerships are in place.
And Dr. Hayes, I guess, is a member of, probably the member of Congress that's responsible for venting more helium. I don't think I could count the number of 500-liter helium dewars that experiments I've set up have vented to the atmosphere. There are a number of approaches you can take here. You mentioned sort of locals, like somewhere in the building, multiple researchers would have a shared helium recycling facility. There are other approaches, for example, just using closed cryocoolers for these research magnets. Which, there are a number of different approaches here. And in addition, there's a class of helium applications where it's simply used as a non-reactive purge. And that's, I think, particularly in a research environment, I think it's going to be very hard to figure out how to sensibly recycle that. In addition, if it gets diluted enormously, then you have to cryogenically separate. I mean, there's a range of applications here. And why is it not best just to let a market price do this to try to figure out which ones of these applications make sense and which don't?
So the types of things that you're talking about require a capital equipment investment that is not necessarily part of the framework for most of us that have equipment from a decade ago, let's say, or further back. So that's the first of the answers. And then why not let a market price account for that? That's outside my area of expertise too, resource economics. But truly, in this era where we have had cheap and abundant helium, we're now in a completely different world. And how do researchers respond agilely to that new reality? That's what you're asking, and we need extra money for research for those of us who are subject to those price fluctuations.
Yeah, and also I think you're a little pessimistic on YBCO and the other high-temperature superconductors. I think a lot of research magnets could be made today with high-temperature superconductors.
I completely agree. All I meant by the statement was just that it is not widely adopted yet. It's not commercially available as a magnet, and it's only in these very specialized centers of excellence that we have in the United States that have really capitalized on that.
Thank you. And Mr. Chair, if there's an opportunity for a second round of questioning, I'd appreciate it.
Sure thing. Mr. Biggs, recognized for 5 minutes.
Thank you, Mr. Chairman and Ranking Member Weber. This has been an interesting hearing. Thank you for your presentations, all of you coming today. Dr. Hayes, I want to just kind of dovetail, if I can, a little bit on the discussion that was going on, because you mentioned the price has gone up I think 450% during your career of helium, which indicates to me that either the demand has exceeded the supply, or you've had an increasing scarcity And I'm assuming that it's the latter that's an increasing maybe it's both, a combination of both. So can you kind of define that for me, why the price has gone up?
The price is related to scarcity, as you say, indeed. And again, this is outside my special expertise, so I wouldn't want to attribute it to any one cause, but certainly we have seen increasing demand for helium worldwide. It's used heavily in the electronics industry, for example.
Okay.
So I think that it's both factors.
Okay, so and one of the ways to resolve it is both the way Dr. Foster said is finding alternatives to helium, and what you've also said is reuse, recovery, and recycling.
Yes.
So there's a third alternative, and this is the part I had known nothing about because I don't know where we find helium. If we were talking copper and molybdenum, I could tell you about that, but I can't tell you about helium. But so. Are there other markers? I mean, when you're finding, when people are exploring and developing, I mean, if we're talking oil and gas, we would know that there's a field. We would be looking at geologic formation. We could kind of accurately, as we explore, we could see how much we're going to have. Tell me about helium. How do we find helium? What are our other markers that go with it? Is it coming with nitrogen? Do we find it with other gases? How's that work?
Currently, we extract helium through the process of extracting natural gas.
Okay.
So it comes along for the ride. It is not in all natural gas deposits. And for it to be economically viable, I understand from others who are in this industry that you need roughly 1% of the makeup of that natural gas deposit. And it's because the natural gas is trapped underground by rock formations, and luckily for us, the helium is there as well. If I may, let me put something into context for you. A single balloon of helium, a party balloon, if I do a back-of-the-envelope calculation on a pad of paper, the number of gas molecules that are there are coming about because of radioactive decay of uranium and thorium underground. That balloon takes an amount of 1/2 pound of uranium that I could hold in the palm of my hand. It takes it 1 billion years to decay on that order. So we are constantly making more underground, but it's an atom at a time. So I favor recycling for that reason, because we just don't want to let it escape the atmosphere.
Right. Very good. Thank you. That's very informative. And I'm glad you mentioned uranium, because I come from Arizona. And in Arizona, we have significant reserves of copper and uranium. And the president and his administration has protected our national economic security from reliance on foreign supplies of critical minerals, ostensibly, including uranium. But we're having trouble actually developing uranium. We're fighting that right now. The U.S. Geological Survey's list of 35 critical minerals encompasses materials, as you know, for clean energy production, nuclear deterrence, and enabling smartphones, et cetera, around the world. But instead of buying from the domestic uranium mining companies, we are looking to China for uranium right now, and other countries. We import almost 99% of our uranium, and that makes it really, really a security risk for us, and that's something we should be aware of. And so I think we should be exploring all those options. And so I'm going to ask each one of you in the brief time I have left, is we've talked about these things. If you can kind of expand and advance the idea of what you use with industry partners, specifically those who might be in the academic world. What do industry partners do with you, and how do they support your efforts? And if you can expand on that for me.
So
Dr. Handwerker, let's start with you.
Yeah,
We'll go this
I'll
way.
start
Okay,
here.
great.
So one of the important parts of the working with industry to see whether something could be economical is we delve into the economics in great gory detail to see what it would take to actually be competitive. And without doing that, then if we fall short, then it's not like horseshoes. It really matters that we have gotten the economics right. And with that, the economics challenges come the scientific challenges, because it doesn't come for free. It's not like we can just marginally change the science to have these breakthroughs. So by working with industry, really from the very earliest possible steps, then we can see what science that has already been developed that we can't use because it has, it falls short of the economic, the environmental concerns as well. And so that's key. And also knowing in the end that we've done everything we could at the point of handoff, at early stage but late enough stage, that we've mitigated the risk for the companies, because without the companies having those risks mitigated, they're not going to be able to get the capital needed to move forward.
And I'm going to recognize Ms. Stevens now for 5 minutes. We can come back in a second round if there's more to be said on that topic. Thank you.
Thank you, Mr. Chairman, for this very important hearing on a critical topic with such great expertise here. I'd like to submit a letter for the record from Umicore. It's a company with operations in my district that is recycling end-of-life electronics and batteries spent in automotive and in industrial catalysts and other metals containing materials that can be recycled. There's also a company I'd like to highlight who I've spent some time with, Solbrain, which produces low moisture and high purity lithium-ion electrolyte. They are the only electrolyte manufacturer in my district for lithium-ion, and the only one in Michigan, and one of 2 in the country. And why the geography is significant is that I represent the country's largest concentration of automotive suppliers, and we're ushering in this electric vehicle wave, but with one in Michigan that's responsible for electrolytes. So I think the imperative and the urgency around today's discussion is quite apparent. Mr. Weiss, your company, it's private company?
That is correct.
Okay, and what's your, if you could share, what's your, revenues or profit or, valuation?
So we sell about $50 million worth of castings per year.
That's great. And you're employing about
260 people, correct.
Fabulous. And you're in the Midwest as well.
That's right.
Which we appreciate. And we're talking a lot about the R&D, but I want to talk about the level playing field. And if you could just shine a little bit of light on that from your vantage point, do you feel like we have a level playing field when it comes to these types of materials and our access to these materials?
Well, we clearly don't. In my mind, most of the materials, or many of the materials, are imported from China,
Have your payments gone up since
that?
you're importing from China?
What's that?
Have your payments gone up?
No.
For what you're paying for them? Okay. They've gone down.
Roughly the same. Roughly the same. So yeah. I mean, there's an impediment there because everything from potentially transportation costs to time to quality of material, and so on. Those are all negatives, and we have the wherewithal to do it in the United States, or we're developing the wherewithal to do that, all in the United States, and we haven't quite done it yet.
And what else could it take to help us develop that wherewithal? What else do we need besides the R&D efforts?
Well, I think you need the R&D effort. I think you need you need customers to help support the work that you're doing, not always buy from the lowest cost producer. So being in the automotive supply market, we understand that a little bit, and so there's a lot of effort into reduce the cost of materials, obviously.
Right. And there's a demand factor as well. And as my colleague, Dr. Foster, talked about, the flexibility for the delineation of what is dubbed a strategic material, whereas that could change. I think we also need some flexibility in terms of procurement. Wouldn't you agree, Dr. Schwartz, in terms of how we maybe maintain or gain access to these materials and the ways in which we go about them and the ways in which we incentivize the potential consumer activity within our own markets?
I do agree with that, Representative Stevens. The United States has plentiful natural resources. We do have rare earths. We do have lithium supplies. The challenge really is overcoming the economics to compete globally. And I can't speak to what other countries' policies are, but when it comes to mining, mining has environmental challenges. And our challenge as a country is to develop clean, environmentally acceptable mining processes. And to this point, that's not yet economical. So it is very challenging for U.S. mining interests to get into that business because it takes so long to get approved for a new mine, because the environmental regulations are what they are, and we as a country haven't yet developed clean mining technologies because there hasn't been a clean mining program out there. So we have lots of challenges. We have the natural resources here. We just need to figure out a way technically and regulation-wise to extract those elements so that your companies in Michigan have all the lithium that they need to produce batteries and electrolytes for a long
And
time.
so they can compete. And
they
while
can
we're
compete.
certainly enthusiastic of the legislation on the docket, I am sniffing that there's opportunity for further legislation. But with that, Mr. Chairman, I remain enthusiastic for a second round of questioning and yield back my time.
Thank you, and recognize Mr. McInerney for 5 minutes.
Well, I thank the chair, and I thank the witnesses this morning. It's really encouraging to hear some of the successes of the CMI. We created that in part because of concern about China's dominating the market, and what we've seen with Japan lately sort of verified that. And they don't seem to have the environmental concerns and regulations that Dr. Schwartz just referred to. And that's a bit of a challenge for us, but I'm sure we can get through it. The one question I have is there an opportunity to Dr. Schwartz or anyone to obtain critical rare earth materials through fracking and or geothermal energy production?
Not as far as I know.
No, nobody has a positive answer on that.
Helium does not come through fracking processes
Right.
either, so I'll just say that.
All right, thanks. Is the difficulty obtaining rare earths, and this follows up with Ms. Stevens' questions, give other countries a critical advantage on battery manufacturing? Dr. Schwartz?
Again, the United States has enough lithium reserves to become a net exporter to the world.
Okay.
Our challenge is, again, the economics of extracting that lithium and turning it into a product that could be sold on the world market. We have the material, we just have to figure out, again, we have to overcome those barriers to the scientific processes of how do we extract the lithium from geothermal brines, how do we extract the lithium from mine tailings. I think we have that. I think we have developed that process. So then the question becomes, how do we do that economically, considering some of the environmental regulations to make that extraction and processing cost competitive on the world market? I believe you are correct. The rest of the world does not have the same hurdles that we do. Our environment is incredibly important and we need to protect it. We need to come up with ways to mine more environmentally friendly.
Thanks. Dr. Handwerker, as each critical material has a different supply chain and a market structure, can you speak to why it's so important that HR 4481 authorize the DOE to develop more comprehensive analysis and market chain?
So first of all of the critical materials are byproducts of some other kind of primary mining operation. And so it's going to be important within HR 4481 to really work with those supply chains, including existing mining in the United States, to be able to extract the rare earth materials that are there at sometimes very low levels. As Dr. Schwartz mentioned, they are there, but the challenge is really how to extract them at these really part per million or tens of part per million level. So the supply chain, and so first of all, in the mining supply chain, we really are looking at the Critical Materials Institute more holistically at which of these different primary mining, copper, iron, niobium, which ones can provide each individual critical material. In terms of the recycling and reuse, yes, each supply chain is going to be different. And so that's why we're focusing on the ones where we can have the highest impact. So for example, for rare earths and hard disk drives, in magnets and hard disk drives, those are, I think we know what a circular economy would have to look like, what the full supply chain would look like. For engines, that's the primary use of rare earth magnets in the U.S. We are working on that because those are very different in terms of products, in distribution. So there are many more challenges for those. So yes, all the supply chains are different, and we have to select which ones to look at.
Can items be manufactured in a way that makes the extraction of rare earths from the recycled products easier?
Yeah, absolutely. So one of the things I'm very proud to be able to report is through our collaboration with Seagate, they now have a task force in determining how to reuse the whole magnet assembly in the next generation hard drives. And the Seagate CEO has said they are going to make hard drives from hard drives, thinking specifically about the rare earth magnets and the magnet assemblies. So yes, they can be, but it really takes the engagement across the supply chain, and I think Critical Materials Institute has played a leading role in that, to show what's possible, how to take the assemblies out, how to put them back into the hard drives, and then if they can't be put into the hard drives, how to create all the different pathways in the supply chain to get them back into new hard drives, starting out from the oxides. So I think that...
As I yield back, I'm going to say that I think Congress should show some leadership in encouraging that behavior in industry.
Mm-hmm.
Thank you. I yield back.
Thank you, and I want to thank our colleague, Mr. Swalwell, for joining us today and offering the legislation that is kind of underlying this hearing. And with that, I recognize Mr. Swalwell for 5 minutes.
Thank you, and I thank the subcommittee chairman and ranking member, as well as Chairwoman Johnson and the ranking member of the committee for holding this hearing and allowing me as a non-committee member, but a former committee member, to participate. This is an issue of great importance to our country, particularly my district with 2 national laboratories and one that I've worked on for many years. And I was hoping, Dr. Schwartz, to start with you. When this bill last came to the floor in 2014, there were some concerns expressed about the impact it would have on government interference in the private sector. And I was wondering if you're aware of those concerns and how you would respond to such concerns.
Thank you for the question. I am not specifically aware of what those concerns are. I have heard that, and there are always debates about what is the role of federal funding for industrial research. The Critical Materials Institute is focused very much so on the early stage research, but we rely on industrial input and guidance as early as we can get it. In many cases, researchers at universities, at national laboratories, think they may know what the whole question is, what the whole problem is, but don't understand all of the corporations' research that have gone on for decades and decades and decades. So having that team with industrial input early saying, you know what, we've looked at that part of the problem, don't spend your time and money there. Having that industrial input to say, you know what, when we look out 10 years, 20 years, these are our fundamental challenges, that's where national labs and academia can play the biggest role.
Thank you, Dr. Schwartz. And Dr. Hayes, you're a great example of the talent that has come out of Lawrence Livermore National Laboratory. And as a researcher and professor of chemistry, could you describe the importance of critical materials, not only to our economy, but also our national security?
Oh, I was not involved in the national security aims at Lawrence Livermore National Labs, but I can, I think Dr. Schwartz may be better able to answer that. But certainly what we have been hearing today is about these many critical elements that come and enable many applications, whether it's for just regular everyday life, new batteries, new types of engines and the like, And also in the national security apparatus, of course, those are exotic materials that certainly are on the list.
And you are familiar with the annual budget for the Critical Materials Institute, which is $25 million. My legislation would raise the baseline to $30 million with the 5% increase each year for 5 years. How would this additional funding benefit research?
So I'm not enabled to comment on that. Again, I think...
Sure, if Dr. Schwartz wanted to
Sure, please.
help us with that one.
There is so much to do, just like there's so much for all of you to do, and there's not enough time. There's so much for the national labs to do, for academia to do in terms of that early stage research. I very much appreciate your proposed bill. The Critical Materials Institute would benefit immensely by having that baseline increased. That would allow us to continue to focus on the most critical elements, or continuing to develop that critical materials framework that will position this country, that will create that enduring capability to address critical materials as new ones come about.
One other issue is our global competitiveness. And within weeks of this bill coming up for a vote in 2014, and we got very close to passing it, China was found in violation by the World Trade Organization for its practices related to rare earth elements. In fact, in this most recent trade war with China, they have sought and have publicly stated that they would use their rare earth advantage against the United States. Can any witness talk about how continuing to invest in critical materials innovation could help us have an edge, or at least get on the same plane as China?
You can start.
So ideally, just like the United States is striving to, and in many cases has achieved energy independence, we would like to have that same independence in everything. We would like to be fully dependent on our own production capabilities, on our own manufacturing capabilities, so that we can make the new energy systems, we can make the new technologies in electronics, and we can make defense systems when we need to make it here. We've lost a lot of that capability, not because we don't have the natural resources here, but because of environmental issues, because of cost of labor. It was more efficient for U.S. companies to outsource. In terms of energy security, national security, I think the United States would benefit by bringing some of that back here.
Thank you to all the witnesses. Thank you to the subcommittee chair, and also thank you to the staff for working with us over the years to bring this forward. I yield back.
And there's been an interest in a second round of questions, at least from Dr. Foster. So Dr. Foster, recognized for 5 minutes.
Certainly, and thank you. Let's see, Mr. Weiss, these aluminum cerium alloys, is there a compromise in the machinability, or are there the advantages all in casting? Is there any downside to these?
No, there is not a machinability issue with the alloy. They machine just as other aluminum alloys do. The one downside that we are working on currently is improving the ductility of those alloys for high toughness type of applications.
And you mentioned that you had a scheme in R&D for the direct reduction of the cerium carbonates.
Correct.
How does that, can you say a little bit about it? Or is
yeah, and we've done this on a laboratory scale. What we do is we inject the carbonates into the liquid alloy under the surface. The speed of reaction...
during the refining of the aluminum? Integrated into
once we melt the aluminum, at least, so we start with a batch of pure aluminum. We introduce the carbonate under the surface of that melt. The kinetics are such that it pretty much instantaneously changes to metallic cerium, and then the aluminum cerium intermetallic. And then based upon the reduction chemistry, we're left with aluminum oxide, which is not a good thing, and then we remove the aluminum oxide without removing the cerium.
So you still ultimately have to get the energy in to reduce it?
Correct.
Okay, all right.
Correct,
Fine.
yeah.
It sounded like you had some magic around that, but still, it's basically a simplification of the process.
It's a simplification of the process. It does not require, therefore, the way we do things
Thank you.
now, which
Yeah,
is
so
to
my-
buy metallic cerium
Right.
and alloy it in.
Right,
Right.
right. Now, do you find that our patent system is serving you well? You know, you're developing all this neat technology, and of course, the obvious worry is you'll develop it all, get it going, and then find that China has looked online at all of your publications and set up a big factory that you can't compete with.
I guess it's always a concern.
Yeah, no, this is something I struggle with all the time.
Right.
You know, that we developed all this great technology, and then because of labor costs or environmental costs or some little advantage, all of the real benefit comes not only in the making of the original chemicals, but the value-added chain for permanent magnets and so on that have strategically been. So, you know, I think ultimately we have to find some way to gently interfere with the workings of the free market here. That the free market has applied, the free market has said, okay, the low-cost worldwide producer of, rare earth magnets is a place where they don't have environmental regulations and they have low cost of labor, and they can, go on the internet and pull all the intellectual property over for zero cost. And so under those circumstances, we cannot sustain a large class of industries unless we interfere strategically with the workings of the free market. Is there any way around that logic that you're aware of? Do we have to, either subsidize or put quotas on imports or something like that to preserve these industries?
From my perspective, the most important part is the research side of it. I mean, as a company that strives to make money, we have to deal with the problem all of the time. And so we have done things like automate our operations and find less expensive ways to do things. And from the standpoint of this direct reduction, we're looking at it. The next step is, can we automate that process to make it as inexpensive as possible so we are relatively unassailable from the international
But then you
market.
depend on the protection of that intellectual property to work. And which is another ongoing challenge. I'll change the subject a little bit. I'm really impressed at the wonderful things you're doing in materials science. How is the situation in recruiting the next generation of materials scientists? Do they all want to go and do, machine learning, AI stuff, or do they want to, I guess a generation ago they went into finance. Are you having better luck that way? Do young kids understand the magic of what you're doing and how it can change the world? Yeah, Dr. Hayes?
I would say absolutely. In my line of work, I'm a spectroscopist, but I'm surrounded by so many young people that are just chomping at the bit to get into these problems, in part to solve issues related to the environment, to climate change and the like. And so the development of new materials is driven by a large sort of...
And what fraction of the graduate students that you all work with are foreigners that we're going to send home when they get their PhDs?
In my program, 50%.
Yeah, that's typical.
50% is a typical number. Yeah. So I have introduced legislation to try to fix that, and I look forward to your support. Well, thanks so much, and I yield back.
Recognize Mr. Weber for 5 minutes.
Thank you. Are we going to be able to have a third round, do you think? Man, where do we start? Quantum computing. Well, let me back up, because I'm on the heel of what Bill was saying. I'm really interested in that, especially when you talk about gently doing something to the free market. So I'm going to go to you, Mr. Weiss. Are you getting, if you can tell us, what's the source of most of your aluminum?
Canada.
Canada?
Canada, yes.
Okay.
Yeah. Because we deal so much in military products, we are actually restricted from buying aluminum from some sources.
Okay.
But nonetheless, we've always bought from Canada, and probably if we were doing commercial products, we'd buy from Canada.
Okay, well, that's good to hear. We're hoping to get the USMCA done, just FYI. So
Yeah.
Thought I'd get that plug in there. I want to switch to quantum computing, because last year was it last year, Hillary, we passed that HR 6227 National Quantum Initiative Act about quantum computing. Are you using, or each of you using any of that? Maybe not you, Mr. Weiss. I don't know, but how are y'all finding that useful? And what percentage, and tell us how that works for you.
So the legislation, I believe, is useful. From a national laboratory perspective, that is providing instructions and guidance to the national labs, to universities, that says the United States thinks that this is a very important direction to pursue. Through the Department of Energy, there have been a number of funding opportunity announcements, a recent one on quantum information sciences. Ames Laboratory won one of those awards on developing new algorithms and codes to work on quantum computers. There is the Energy Frontier Research Center program through Basic Energy Sciences within the Office of Science, Ames Laboratory, and many others recently won a new center award to develop topological semi-metals, which have the potential to contribute to quantum information science.
So you're not there yet, but you see it coming.
So there are quantum computers out there. Ames Laboratory does not have one. You can purchase a quantum computer, I think, through a company in the state of Washington. A number of labs do have those existing quantum computers where they are trying to further develop the capabilities.
Okay, and do any of y'all, and this could be for you too, Mr. Chairman, and you too, Bill, it seems like a week ago in the news that China cut off exports to Japan of a rare earth mineral or essential element. Did anybody pick that up in the news? No, does that not make sense?
I know, back in roughly 2010, China cut back the rare earths for magnet purposes to Japan. As some, I can't remember what they were fighting about. But
Yeah, I was thinking like in the last week of news, I saw it come across my Apple Watch.
Well, I'm sure
things.
it's
Yeah.
a threat there that's all the time in
But my watch or the
bilateral
trade
negotiations.
thing?
No,
Yeah.
the Chinese threat. They know
Right, I
it's
got you.
by the throat here.
Okay, well, I don't know if y'all were paying attention or saw that. So here's an interesting thought. In your discussion, Dr. Hayes, with Mr. Baer earlier, you talked about escaping using liquid helium and stuff like in some of the high heat areas. I'm thinking, how about waste heat recovery in those applications? Has any thought been given to that?
To the best of my knowledge, I do not know of that aspect being capitalized.
No? Anybody else?
I will point out that in the production of aluminum cerium alloys, which is my thing, that the formation of the intermetallic is exothermic, and therefore the total heat content per pound of aluminum melted is lower in the aluminum cerium alloy system.
So that's not necessarily. In some of Dr. Schwartz's testimony, he said that CMI researchers discovered a way to reduce the processing temperatures from 3,100 degrees centigrade to 800 degrees centigrade through electrolysis in a molten salt. Do you know what those correspond to in Fahrenheit, 3,100 centigrade?
Let me get back to you on that.
Okay. You're supposed to know these numbers right off the top of your head. No heat from this end, pun intended.
That's the National Energy Technologies laboratory work
Okay.
that I'm less familiar with.
So in those applications, there would be some possibility of getting waste heat recovery?
I suspect the answer is yes.
Okay.
Department of Energy, colleagues of mine have been discussing how to take advantage of waste heat for the last few years.
Right.
And I believe there are relatively small programs funded through DOE, but this is an area that is ripe for additional research. If you look at those Sankey diagrams that show where energy is going, a tremendous amount is going to waste heat, and there are opportunities to do something with that, whether it's create electricity or just put it back into the process for metalworking, for example.
Right. Well, I would suspect that the latter of those two would be the more friendly for for what you're doing, as opposed to try to put it to the grid. But anyway, these things just fascinate me. So I'm over my time, Mr. Chairman. I appreciate that. I yield back.
Recognize Ms. Stevens for 5 minutes.
Thank you, Mr. Chairman. Dr. Hayes, can you talk about the ways in which you work with federal agencies and which agencies you work with in your helium recycling and storage efforts?
So the National Science Foundation is the major one, of course. I am also funded by the Department of Energy, so they are concerned about these aspects. And then at times, I've been fortunate to be invited to a helium users meeting here in DC, and that involved the Defense Logistics Agency showing up and discussing. So I would say those are the three primary ones.
And I know you talked about this in your testimony. NSF is a funder of yours, and do you know through what programmatic division NSF funds you?
Yes, so math and physical sciences, and specifically the Division of Materials Research, and also a couple of other ones.
Yeah.
Yeah.
And do you know the average annual allocation of award that you're getting from NSF? And how strict are their boundaries for which they're funding you on?
So a typical grant amount is a 3-year grant, and the target amount is on the order of $360,000, so $120,000 per year in this program within the Division of Materials Research.
And so none of that goes towards labor costs?
Some goes towards labor, absolutely. No, graduate student labor and maybe a little bit of summer salary in my case.
So no one's getting rich.
Oh, no.
Off of that. And so they're primarily funding you for the research side of the efforts, but nothing for commercial application, along with DOE, nothing for commercial application?
There are 2 programs that I've participated in. One is the Energy Frontiers Research Centers, as well as the CCI, Centers for Chemical Innovation through National Science Foundation. Both have had strong emphases encouraging us to go into commercial directions. So there are small business partnerships that are nucleated and that sort of grow out of those large team assemblies. But as an individual researcher, it's extremely hard on academic timescales to partner with industry. We'd
Right.
like to, but it's difficult.
Which we have respect for that. Doctor, the remaining 2 of you that I know are directly tied into federal research endeavors. Do you mind just talking a little bit about your work with NSF? I know, Dr. Schwartz, you had mentioned NSF in your testimony as well.
As a Department of Energy National Laboratory, we get 0 funding through National Science Foundation.
0.
0 funding, and that's good. We're a Department of Energy National Laboratory. One advantage that Ames Laboratory has is we sit on the campus of Iowa State University, the only lab that actually sits on a campus. And many of our joint researchers are joint faculty members, and they develop understanding expertise, students and postdocs through NSF, and sometimes that work is very relevant to the more mission-oriented Department of Energy research.
Yeah, and you're able to have access to it, which is great. Yeah,
Very important, yes.
yeah. Thank you.
So I've worked extensively with National Science Foundation. I've been at Purdue for 14 years. I've had major interdisciplinary programs in sustainable electronics, which thankfully I've been able to keep up those contacts in sustainable electronics. They were also part of hard disk drives. So we could bring some of these key contacts into not only in educating our students, but also in connecting the technologies that they're developing, the science they're doing, into actual practice. So in one program, it ended recently, we had 30 2-year or 3-year fellows, all U.S. citizens who got their PhDs working in this program.
Yeah.
So, yeah, we work extensively with it. The other thing is that in the action number 6 of the strategic plan, the President's strategic plan for critical materials, it is specifically focused on workforce development. So I've been talking, and others at CMI have been talking with people at NSF who are in charge of this workforce development piece to see how we can actually expand the reach for critical materials, mining, recycling, substitution into NSF.
Right. Well, Dr. Handwerker, we also want to commend you for your educational background, including, what is it, a Bachelor of Arts in Art History?
Yes.
And now a PhD, scientist with, and you're also working with NIST as well, is that?
And I'm also working with NIST very closely.
Well, what our chairman might know is that on the subcommittee, which I chair on research and technology, which has oversight of NSF and NIST, we're glad to be good funders of the rare earth materials and materials work that all of you are doing, and want to make sure that that makes its way into future legislation, and that competitiveness and productivity and jobs are at the forefront. So thank you all so much. I'm over my time, but this was obviously a good one. I yield back, Mr. Chairman.
Thanks. Dr. Baird for 5 minutes.
Thank you, Mr. Chair, and this round of questions is going to go to all the witnesses, but this is going to be a ladies' first round. So, but I want to know what policies that Congress, the Department of Energy, and other relevant federal agencies might do to encourage industry-led research and development efforts, critical materials research, and so on. But before we do that, Dr. Hayes, I noticed in your testimony that this is the International Year of the Periodic Table. Is that 2018 or 2019?
2019.
So anyway, I noticed that helium was on the second element on that, and then you also mentioned that it's very, very small, and it can escape anything. Helium can escape anything. So I was wondering if we're doing any research on some kind of container. I'm just kidding you. So anyway. But back on the question of what policies could Congress and Department of Energy and so on, other federal agencies do to encourage industry-wide research and development. So, Dr. Hayes.
I would start by saying basic research funding has been a challenge over the time of my career. And, I think we need to see increases in that basic research funding and also encourage ties to industry and finding mechanisms to do so. 3-year grant cycles make it difficult to achieve those things. I might highlight, tied to supply chain issues, this is maybe outside the purview of this committee, but just to highlight that the strategic helium reserve that is being privatized in 2021, here we have an abundant source of helium, one of the top 3 producers worldwide. You mentioned a container. That is one of the only containers for helium. It keeps it underground, yet we're about to sell it off to a private company that may belong to a foreign entity. And so even though that's outside this committee's purview, I think that that's something to keep in mind. So what can Congress do? Maybe keep the container, keep our production capacity of something that we are a leader worldwide. So I'll let others respond with that.
So another important part of research in moving it actually into commercialization and creation of a supply chain is that it goes from research, development, and demonstration. And what we found in many cases is that we're not serving our country well by throwing the technology, the science over the wall and expecting then industry just to be able to take it forward without additional scientific help as they move forward at the demonstration, the development and demonstration stage. So I think that could be one important policy emphasis in making sure that we maintain those connections during the commercialization stage, because in this technology readiness level, 1 through 4 is the early stage research. To get to commercialization, you've got 5 through 9, and that is where that valley of death happens. And the valley of death happens frequently because something wasn't determined in the early research stage, but if they had access to that research capability, then they could overcome it.
Thank you. Dr. Schwartz.
So there are big companies, very large companies, that do fund critical materials research. CMI partners with a number of them. Ames Laboratory partners with a few others, and I know that there is significant investment by some of our largest companies in critical materials and other research. Small companies don't have the resources to do that. They simply can't afford. Those small companies often have access to small business incentive programs for jointly funded research. I think that if there are ways to incentivize industry to come forward, to U.S. industry to come forward and say, these are what the biggest scientific challenges are going out 5 years or 10 years. That would be the areas that universities and national laboratories could have a big, big impact on. In terms of specific research, in terms of a specific hurdle in order to become profitable or to make a larger impact on the global supply chain, I'm sure policies could be put in place that would, something that Representative Foster maybe alluded to. Are there ways that Congress or the United States could make U.S. companies more competitive in the industrial market, in the international market?
Thank you. And Mr. Chairman, could I have Mr. Weiss comment?
Yes.
Yeah, I think it's important to emphasize what Dr. Handwerker said about the industrial collaboration. We see TRL levels are supposed to always go up over time as research continues. That's not always the case. You sometimes get it up to a 7, and then you miss a critical piece, and you fall back down that chain again. And so at least there is a role for some research in the later stages of development and commercialization, and I think that's very important. The other comment that I have is the way that the CMI system is set up. It's a bit of a dream team because there are people at the academic institutions and at the national labs that understand some fundamental business economics. So when we have our weekly calls on our program and someone suggests something and I say, you can't do that because it's going to cost you $2 a pound, there's an understanding that even though it's a great idea, it's never going to go anywhere. And so we cut off those dead ends very, very quickly by having a very close relationship between the researchers and, in this case, ourselves. Thanks.
Before we bring the hearing to a close, I want to thank our witnesses once more for coming all the way to D.C. to testify for us today. The record will remain open for 2 weeks for additional statements from the members and for any additional questions the committee may ask of the witnesses. The witnesses are now excused, and the hearing is now adjourned.